Good afternoon, ladies and gentlemen. Welcome to the HKIAS Distinguished Lecture presented by Professor Lyons. And may I please invite Professor Li, our Associate Vice President of Strategic Research, to give an opening speech. Thank you, Professor Li.
Thank you, Jackie. Very welcome again, everyone. Professor Lyons, distinguished guests, colleagues, and students, good afternoon. If you are here this morning, I would like to extend my welcome to you again. It is my great pleasure to welcome you to the special distinguished lecture series of HKIAS, part of the 10th anniversary celebration of HKIAS at City University of Hong Kong. So I will repeat some of the parts that I said this morning, okay? Since establishment in 2015, HKIAS has grown into a global hub for groundbreaking research and collaboration in science and engineering. Over the past decade, it has united world-renowned scholars to mentor young researchers and inspire innovation. Today, we are honored to host Professor Pierre-Louis Lyons, HKIAS Senior Fellow, the Chair of Partial Differential Equations and Applications at the Collège de France, a recipient of the Fields Medals in 1994, and the Grand Prize Ampere from the French Academy of Sciences, and a number of numerous prestigious honors. So in this lecture titled On Mathematics and AI, Professor Lyons will explore the connections between these fields and share valuable insights into their interplay. So I would like to say thank you very much, Professor Lyons, for sharing your expertise with us today. And thank you all for coming here, joining us in this celebration of knowledge and discovery. So may this lecture inspire us to push the boundaries of mathematical inquiry and explore new frontier. So now please join me in warmly welcoming Professor Pierre-Louis Lyons.
Okay, it's working. Well, thank you very much for this kind introduction and those kind words. Great pleasure to be back here. I am back here. It's like, you know, coming home every year. And this year it was a little bit special because I was this event with the IAA in March. And it has been quite, I've been coming here for many, many years. And in particular, I've had the opportunity to, that's the last, you wish. You wish we were there, namely the last slide. Anyway, so since I've been giving quite a few of those lectures here, I decided this time to take a lot of risk. So I need to apologize for giving a talk where I'm not sure, in fact I'm sure that I don't. I'm not sure I understand the topic, and I'm not even sure I know the topic. A consolation is that if people pretend to know what AI is nowadays and pretend to follow what's going on, basically they are lying. Because when you see the number of articles that every day goes out on AI, it's just impossible to track it. Okay, you can use generative AI to analyze the papers on AI, but that's of course a little bit dubious. Okay, so sorry for that. It's going to be some kind of you know, we are going to go across many, many topics. There will be essentially no math. I think that's much better for essentially all the audience. So I'll begin with general facts. A need for math, this is also always a question mark. Whatever the subject, you will always find people saying, we don't need mathematicians, and other people saying, we absolutely need mathematicians. And here it's exactly the same, but I will discuss a little more this issue. And I will finish with some pet research projects of mine So this is not a Candide point of view, it's a Candideuse point of view. So I will ask some, maybe with sometimes a little bit of irony, I will ask some naive questions about quite a few subjects on AI. So let's begin. General facts. First of all, I hate the terminology AI, okay? Artificial intelligence, I never use it. So AI, at least one can forget about intelligence. I much prefer natural stupidity than to artificial intelligence. But the point is that basically what we have is machine learning, or to be more specific, because even machine learning is ambiguous, statistical machine learning is slightly better. The point is that in my view, at least 3 fields, different fields, merge into statistical machine learning. One field, obviously, is statistics and data analysis. From time to time, even mathematicians are not very despise statistics, not really mathematics. Well, I want to point out 2 main mathematical discoveries made by statisticians that I will use later on in the lecture. One is the theory of random matrices, and the first one was Wishart, a statistician who built a correlation matrix based on a rectangular matrix composed of independent random variables. So covariance metric to be very specific, and computed explicitly, in the case of Gaussians, computed explicitly the law for n by m, so they are rectangular matrices. Later on, of course, we all know Wigner's magnificent discovery about the half circle law. His motivation was entirely different. Wishart, you know, covariance matrix, statistics, natural. Wigner, and I think we should ask Serge, but what I read was that puzzled by the apparent disorder, chaotic nature of atomic spectra, wanted to have a simpler setup, namely matrices. Okay, we learn about infinite matrices in the Heisenberg, that was the Threeman paper this morning. So a simpler situation where we could see the emergence, where he could see, not we, where Wigner had the intuition that some kind of universality might emerge. I also want to mention Dyson, who made a proof which is essentially a complete mathematical proof of Wigner's law. Okay, first mathematical discovery, large random matrices. Second mathematical discovery made by statisticians, Wasserstein. So Wasserstein metrics, which are quite natural from a probabilistic/statistical point of view, extend one particular case of a metric, which is the so-called Monge-Kantorowicz distance, and pave the way to what we could call nowadays the analysis on the set of probability measures. And I will come back later on. Other ideas that emerge in data analysis/statistics are very interesting algorithms. One is the so-called EM algorithms. To simplify is suppose that you have a distribution. How can you represent it best by a combination of 2 Gaussian densities or 3 Gaussian densities, whatever. First field, statistics, data analysis. Second field, computer science. So if one wants to trace back AI with some contribution, I certainly want to quote one of my favorite scientists of all times, namely Ada Lovelace, Byron's daughter, which was the first programmer in the history. She wrote down a program to compute the numbers composing the Fibonacci sequence. What's quite amazing, if you think about it, is that she made these algorithms, but the computers didn't exist. Babbage was still trying to get funds. I recommend the lecture of his book, Memoirs of a Philosopher. There is absolutely no philosophy. It's actually just an accountant saying, well, this week I got a promise for £80. But he had this magnificent idea of the difference engine, but he never materialized. But Ada Lovelace produced a program for this non-existent machine. Even more important, she was a visionary because she said that those machines, again, that didn't exist, should be able to handle everything that can be made numerical. And she explicitly mentioned sound, text, images, which is absolutely amazing if you think about it. Okay, she was Byron's father. She was Lord Byron's daughter. Apparently, she never saw her father. But her mother was a very gifted mathematician, in fact, it turns out. So mathematics ran in the females of that family. So that's before neural networks. That's a very important vision. And she explicitly asked the issue of trying to reproduce the natural intelligence on those machines. Absolutely amazing. Much later on, in the 60s, so I see many young faces who were certainly not born at that time, but in the 60s, computer scientists become very, very excited by the idea of going into some kind of numerically based intelligence, or slightly more complicated. At that time, people were using much more terminology like expert systems, and this was essentially a global failure, except for two things, which are two programming paradigms. One is rule-based programming, expert systems, and the other, which I like even more, is constraint programming, or programming by constraints, which can be very useful when you have a problem where you have a huge number of constraints. You would like to get the best solution, but you're already happy of finding one solution. Okay? And so this is a typical way of finding one solution, which is quite efficient numerically and digitally. Think of air traffic control as an example. Even more recently, you had in computer science something already called machine learning without any kind of neural networks. And a prototype is the algorithm to build k-means, which is how to decompose in an Euclidean space, important, not absolutely necessary, but important, how to decompose a big set of data in zones with the lowest possible number of barycenters, roughly said. Okay. Third field, in my view, are numerical computation. Okay, so as is customary, one can go back to von Neumann. In fact, most of the machines that we are using nowadays are von Neumann machines. Then in the 50s, numerical methods emerged, first finding differences, and then very quickly, in order to handle better geometries, more sophisticated numerical methods like finite elements. So it started with engineering to math, and in mathematics, for instance, if you think about the finite element methods, a pioneer was Babushka, and Philippe was a very important scientist in that direction, which is how to make sense of finite element computations in numerical analysis. So this was clearly a success, and mathematics went all over the place in finite elements and related methods by explaining what's going on, introducing stability conditions, even in the generation of meshes, how to generate in 2D lots of triangles to cover a geometry. In fact, there are mathematics to do that, marching schemes. So, but then HPC got a little far away from mathematics, and it turned into a race, which is who has the biggest machine, okay? And to handle larger and larger problems, couple modes, losing also at the same time, losing control of the accuracy. It's not okay to say that with neural nets, we are doing numerical computations, that it is the first time that we are doing numerical computation without any notion of precision. If you think about those huge codes, how do you check those codes? I mean, think of climate prediction. Huge codes. thousands and thousands of lines, a huge of subcode and so on, lots of parameters. How do you check? Well, essentially, checking those codes is done by comparing one to another one, which has been built along the same principle. So there are serious issues one might ask there. Okay, one can also do some kind of historical backtracking. So even in traditional numerical methods, we saw this phenomenon of losing control of what was going on mathematically. Of course, the race forward to the biggest machine, in some sense, got sidetracked by parallel and cloud computing. Okay, what about neural nets at the intersection of these three fields? Early days, of course, we all know the name of Hopfield, who in fact got a Nobel Prize about that quite recently. But I would like to mention another name on top of Hopfield, Amari. It is not our Habib Amari. It's a much older one, and he is Japanese, in fact, this Amari, who in fact had the idea of the backpropagation. So essentially, as we will see later on, you have a neural net, so think of nodes. Computations flow from one layer to another layer that form one node. And in the numerical solution of the optimization, there is a possibility, especially when the neural nets are quite large, to do a backward propagation. Mathematically, we know what that is. This is just the adjoint state going backward, like in the calculus of variation optimization, and it's a propagation of the gradient, or something like the gradient, which of course measures the sensitivity with respect to the things that you are using to minimize. Okay, that's what it is. Of course, those people had absolutely no idea of. So it was a very, very brilliant, and that's absolutely crucial to learn why. We'll see that a little bit later. It's not new. Backpropagation, 86. This fundamental idea for learning is 86. I saw many applications of, no one would talk about deep neural nets, of shallow, as we should say, although no one knows what is shallow and what is deep. Applications in the 90s. In France, one guy coming from probability, Robert Hazencote, was a pioneer. And in fact, I remember in the early 90s listening to one of his talks where he was doing, using neural net, the automatic classification of submarines. Okay. In fact, I saw also, because this will tie with what I'm going to say later on, I also saw at INRIA examples in order to help people in wheelchairs in order to walk with exoskeletons. So quite, else, numerical classification already in the 90s. But then something happened at the technological level, the so-called GPU, graphic processing units. Okay, so you have various sorts, the TPU, the NPU, as we say from time to time, which allow to handle bigger and bigger neural nets, bigger and bigger sets of data. So roughly, you can think that a layer is composed of a bunch of neurons. Think of a line with a bunch of neurons, nodes. You have a relatively simple operation from one layer to the next one. You are going to propagate numerical values, which can be averages, hard and soft truncation. The transformers are also pieces of a neural nets, layers of a neural net, which are very useful for the large language model, but that's the operations themselves are simple, but there is some kind of feedback loop that I don't have time to explain. And all those operations require weights, unknown weights, which are to be determined. Fine, so that's what it is. The training part for a sense of classification or weather data and so on, you have a connection, you have a bunch of data, and you have defined the architecture of your neural network. So layers, neurons type of operation, that's the architectural part. So you can propagate numerical values from typically one piece of your data, and once a learn has been made, one element of your data. It has been analyzed beforehand, so you know what for this data, what the answer should be. You compute, you see the error with what it should be, that's a loss function. Given weight, how far are we from, how far are the results from what we know? So often people take least squares. If we think about equations and so on, this can be a very bad choice, but traditionally that's least square. And then we try to minimize, to determine the best possible weights in order to be as frequently as possible to get the correct answer. So techniques are stochastic gradient descent to find the best weight. By the way, essentially you immediately see that the result, the numerical result you get in the end, after you have chosen the weights and so on, is of a stochastic nature. So you shouldn't expect, if you run twice the same program, to get twice the same result, okay? No problem with that. So training is extremely consuming in terms of energy and resources. When the weights have been determined, I'm not talking about generative AI, where a simple request on ChatGPT can be quite consuming in terms of energy, water. It's because of data centers. You need to call the data centers. It's not so much the algorithm. So the energy consuming, and also it raises human issues, because you have this huge collection of data on which you're going to train your algorithm. Who is going to make the annotation? Okay, for ChatGPT, no one knows where the numbers of people, you know, the little ants that have done the tedious work of annotating everything. So it turns out, it seems, that people in jails in Finland were used, which gives some kind of bad memories of that. Okay, they were paid. And also people in Africa, the second part of my previous statement might not be entirely true there. They were probably paid a little bit. This is not sustainable, okay? So this is why also when OpenAI tries to retrain, they are using lots of technique in order to not to have to start from scratch. And in fact, they are hiring young mathematicians in order to be a little smarter to retrain. So the electricity consumption of all this numerical universe we are living in is getting crazy. A few years ago, it was the rule 4 + 4 = 8. That's the correct operation, which meant that it was more or less distinguishing between the various sources of electrical consumption. That it was 8% was what the numerical world was consuming in terms of the total energy consumption in the world. Now it has, we don't even know the numbers. And you can try to make perspective in 2030, 2050. If we don't work differently, it's not sustainable. We are not going to use all the energy, all the electrical production just to have AI, okay? So need for efficiency and frugality. So in some sense, other competitors, generative AI is the worst, right? So I won't be talking much about generative AI because this is introducing even more unknowns in a situation that I barely understand or even know. But it's clear for me that we need to be more efficient, more frugal. In some sense, it's exactly what happened in the arms race between Russia and the USA. The USA are all the biggest machines. They could make all the simulation they wanted to build planes and so on. Russians had very few machines, so they had to work. And so they had, in fact, applied mathematicians. We know quite a few. You met quite a few, Philippe. And so they were replacing, indeed, they were replacing the power of computers by the power of their brains and the fantastic Soviet schools at that time. Okay, it has changed quite a bit. So, which is, by the way, a proof that mathematicians can be useful. Russia didn't have computers, but they had mathematicians. And they competed. Okay, they were behind, but in the space program, that's debatable. Okay, need for efficiency, frugality, and if you want to do better, you'd better understand what you're doing. Simple. Drawbacks. Okay, so bias in the data. So there are, of course, whenever you have a problem, engineers are very gifted at finding cures, solutions, ad hoc solutions. So oversampling is what is known, but bias can be a terrible thing, and there are many examples. I still recommend the book by Cathy O'Neill, Weapons of Mass Destruction, Mass, M-A-T-H, okay? It was about data much more than about AI, but that was already present. So the bias in data is a very serious issue. Okay. This morning we had this slide of 43 Nobel Prize winners. Okay. No, that's very interesting because give this as a data and ask him, now present 3 photographs, 2 men and a woman, one man wearing glasses, one without wearing glasses, and the third is a woman. Who has the best chance to become a Nobel Prize winner? I doubt very much that any kind of trained machine, will choose the woman. That's a typical bias. I'm, of course, oversimplifying the picture. You can think about all minorities in general. And that the bias, in fact, destroys minorities. That's a very well-known fact. And oversampling is how to correct this bias for minorities. So it often works. What does that mean, works? That's a little bit complicated, because if you rerun, you don't get exactly the same result. Benchmarking, it's quite difficult because you don't keep track exactly. People are not always transparent on how many GPUs they are using, and so on and so on. Not always. There is a famous, what I call the G effect. It has nothing to do with the G point. It's the G effect is about the name after Groking, which is an engineer. So finally you understood. Took you some time. The G effect. The G effect is named after a guy, I think was his name Groking, and it's something that happened where some people, I don't know if it were at Google or somewhere, someplace like that. They had a run, a neural net run, and they forgot it. So they saw the result they were getting, which was okay, without being exceptional, and they forgot it for about a whole week. And when they came back, they realized it was still running, and the result was 10 times better. I mean, 10 times is, okay, what's happening? Of course, if we are thinking about local minima and say, okay, it took time to get out of some local minima and get, but that's too simple. There are more complicated effects there. Not reproducing, not reliable. We all know that there are hallucinations in generative AI, but I don't want to spend too much time. And all this is because we do not fully understand how it works. I said we. I should say I do not fully understand how it works, but I'm not the only one, as John was saying. Social issues. That's a very important topic, on which I could go on and so on, and which would deserve not only a meeting, not only a talk, but a meeting on such subject, because that's a very important subject, which is natural every time you have a new technology and some kind of new technology that invades many aspects of our lives. So there is the issue of trust connected to reliability, and the issue of privacy. There are many more. I don't want to go there now because I think this is a very serious issue on which IIA might be a I'm sorry, our institute might be a serious place to discuss about it. About privacy, I want to mention, after all, we are in China. I want to mention something that I read in Peter Neumann's book, which is written in the 80s or 90s, which is computer-related risk, who quotes an old Chinese saying that goes, if you don't want someone to know what you are doing, don't do it. And the same is true to nowadays, except that you may replace someone by everyone. Okay? So that's a cure, which is, of course, a very brutal cure. But I find this quite illuminating, that if you think that quite a few, maybe 1,000 years ago, there was already this issue about privacy, which means that's a fundamental aspect of human societies, because people were already thinking about it. So nowadays it has exploded. Okay, a few trends. Application to sciences. In fact, I'm much more convinced by applications of AI to science than many other applications. Chemistry, you know better than I do, Nobel Prize in Chemistry for what Google DeepMind, at that time it was only DeepMind. They were already a subsidiary of Google, but Google was not present in their mind. Health and medicine, that's absolutely amazing the way it's blowing it, and it might really help society, especially in the countries like France, and I'm pretty sure that it's true in many, many countries where we don't have enough doctors. Okay? Health and medicine, meteorology, climatology, about, when was that? A few months ago, we had a whole day organized with Stéphane Mallat, a real expert, not like me, a real expert in neural networks, well, in AI, much more enthusiastic than I am. We had a day on climatology, new numerical methods, understanding neural networks, for climatology and meteorology. I was really impressed by quite a few talks, but I was really impressed by the two teams from Google DeepMind. The team by Tony Lam and the two teams, let me forget, there are too many names I would need to quote. Tony was the first that made meteorological computations, about 2 or 3 days predictions, which were as good as any meteorological center in the world. Okay? His claim, and I joked about it with him, his claim that we never use any equation. But first, if you look at his layer, he took the sphere, I mean the Earth, not quite a sphere, he took the Earth and built his neural networks based on some kind of discretization of the sphere. So already his geometry was there. And then it's true that he took all meteorological data and so on, and didn't write down any equation. But another team at Google DeepMind did much better. They improved all those results. They're doing much better by 20 or 30% than the best results worldwide, and are going to 10 days prediction, which is essentially the borderline in terms of what you can accomplish in terms of meteorology. And how they did it? Hybrid AI, so I think that's a very important in scientific application. So what they did was they use basically, if you think of climatology, if you think of meteorology, climatology I don't have time to discuss. If you think about meteorology, you know the basic art of the equation, Navier-Stokes equation, if you want to simplify, well understood, okay? But this is not enough. You cannot do meteorology even if you know the initial conditions that you don't know, which is another matter. This is not enough. So they use traditional numerical methods for this art, and all the rest that you add, which are tuned to take into account the effects of clouds and so on, this was done using AI. So all the things where traditionally you would put parameters and start optimizing the parameters, you use data to optimize this, the black box. I think this is a very, very important way to go. In the private sector, okay, people talk a lot about generative AI. Discussing with companies, I don't get the same feedback about the use of generative AI. So potentially it will reduce the number and the role of lawyers, consultants, and so on. I'm not going to cry. But it's certainly not a fast revolution that people were talking about 3 or 4 years ago. It's there. We'd better understand it. We'd better, in some sense, if you want to control, if your aim is to try to control it, you need to understand it better. It's very difficult to control something you don't understand. Mathematically, neural networks are also very interesting in order to do numerical computations in high dimension, model reduction. We were able to solve in that manner a PDE in infinite dimension on the space of measures. And also analyzing that there are indeed reduced model in a lower dimension that could do the same job. So that's model reduction. In fact, there are numerical computation in high dimension are often doing okay using neural nets, because in the end, the solution doesn't really depend on a huge number of dimensions. The explanatory variables should be relatively few, except that you don't know what they are. And they may not be linear coordinates. Could be much more geometrically oriented. So the question is, okay, we can do the computation because the dimensionality, the true dimensionality is much smaller than what appears. But can we go further and try to extract out of those computations what really matters? On some example, we were able to do it, but we had the economical interpretation helping us. Need to understand, need to be more efficient. Mathematics, I already mentioned that. What do we know in terms of math about what's happening in those black boxes? Stochastic gradient methods, collectively mathematicians understand them quite better. Very interesting is the fact that in terms of approximation, interpolation of function, this relation related to what we call approximation theory and harmonic analysis. And I like very much the work in that direction of Helmut Bolsker at ETH Zurich, that in particular shows that we have many kind of approximation tools, splines, whatever, and it does at best on all categories, on all fronts, than what we knew. Devaux has some very interesting paper also about this subject, trying to understand. Also, especially when we are dealing with image, in some sense you want to move an image to another one. This is exactly the Monge-Kantorowicz problem of moving sand from one place to the other. In mathematics, that's called optimal transport, and we have quite a lot of mathematical understanding. And the last piece that that is being used, which is useful, it's a theory of large random matrices. I mentioned that with Richard Wigner Dyson. And the connection is that if you think of the loss function, you can take the matrix of second derivatives. It's a nation. There are many random terms, so can maybe, and it's being used for the theory of random matrices. Okay, so about models, because in some sense, those mathematical theory explain bits of what's happening in your network. What about the global picture? How does it work? So there are many attempts using min-field dynamics, min-field in the sense of statistical mechanics, statistical physics, and or min-field games, my favorite theory for multi-agents reinforcement learning. And there are also some interesting observations that explain pieces of the global picture. There is a fantastic, beautiful law, estimate, formula by Johnson and Lindenstrauss father. So in Lindenstrauss family, you have the father, the mother, the two sons, one of which Ellen got the Fields Medal, and also an uncle. Okay, so it's even worse than the Bernoulli, and all at the highest level. But anyway, that's the father in the family, that's the father law, which estimate. And this, even if you're not mathematically oriented, you should be able to understand that. So you want to pick in Rn, so your n dimension, you want to pick k almost orthogonal vectors or points in the spheres. Okay, orthogonal, we know what it means. Almost orthogonal is that the scalar product, the absolute value of the scalar product is less than epsilon. So if we take exactly orthogonal, we can find more than n in n dimension. That's an orthonormal basis. But if we throw in a little epsilon, how does it change? In small dimension, not much. 2D. We can do 2D. 2D, take the circle. You pick one direction. So the other has to be, let's say the vertical one. The other has to be in epsilon neighborhood of the horizontal axis. And if you pick one, you cannot take a third one. So you have two. In 3D, similar geometry, it's only 3. But if you go higher, then the maximum number of epsilon orthogonal direction, the log of it behaves like epsilon n square. So it behaves as the exponential of epsilon n square. So as the dimension grows, so those are typically what I was saying about analysis in high dimension. As the dimension grows, you can pick a huge number of epsilon orthogonal direction, which is also, in fact, the way which is useful is that you may have a huge number of information, but in fact, it lies in a very low dimensional space. Okay, so it's the other way, which so that's why people have also built on that, have algorithm to get the minimal type representation. There are okay, so that's the best proof is the Johnson-Lindenstrauss law lemma formula, and at least 2 Fields medalists in their respective blogs have proposed different attempts to make the proof. One by my colleague, Tim Gowers, who in his blog or exchange it said, well, okay, so typically when you pick a direction, you are excluding for the other picks, you are excluding a certain spherical cap. Okay? Now compute the volume of the spherical cap, which for Tim seems an obvious exercise. For me, it's almost impossible without making 10 mistakes. So it's clear it goes to 0 very fast, so that's why we should have more and more room to throw in new directions. Terry Tao proposed another solution which doesn't give the best result, which is already much closer, and the idea is that if you take 2 points randomly on the sphere, as n goes to infinity, they're almost orthogonal, okay? Law of large numbers. And so the typical size is, of course, in term expectation is 1 over square root of n, because the sum of the xi square is 1, and there are n of those guys. So and they are by rotation invariant, they're all the same. So the expectation of x1 square is 1 over n, okay? 1 over square root of n, but the deviations are going to be Gaussian tails, hence the exponential. It looks like a large deviation result. We miss the 0, which is the limit, by epsilon, and then we have large deviations, and that's what it is. In fact, that's proof, that's Johnson-Lindenstrauss proof, which is about concentration of measure and large deviation from concentration of measures. Okay, that was my 2 minutes math to see that there are fascinating mathematical problems that comes from this. And I conclude very briefly with some pet research of mine. One is that many of those problems keep the invariance by permutation of the labels. So the neurons are being labeled 1, 2, 3. But basically, you can say that instead of 2, you have 3. Instead of 3, you have 1, and so on. So you have this invariance by permutation, which means that if you do all those permutations, what you have is a loss function, quite often, which is symmetrical. And that's a catastrophe from an optimization point of view. Because if you minimize a function, you may get lucky and have 1 minimum or a few minima. But if you have a symmetric function, then as soon as you have 1 minimum whose coordinates are different, then you're going to get a lot of other minima. So that's a catastrophe. So clearly, built in the algorithms, there is some kind of random perturbations which allow to do some symmetry breaking. Can one work a little more efficiently about those symmetry breakings? So on simple tests, we did that, and the speed up was factors of thousands and so on, but on very simple tests. On more complicated tests, it's not as clear because quite often the invariance by permutation at some point is broken. One direction. An even more mathematical direction, I might be the only one in this universe interested in that direction. Would that make any sense to compress neural nets? What does that mean? It's not compression of the data, it's compression of the architecture. And for this, I need to take an analogy with classical particles. So we know Newton dynamics for n classical interacting particles. And we know that n goes to infinity. You know, mean field. You have mean field regimes, sometimes called kinetic models, like Vlasov equations and so on. Mean field equations, because quite often, provided, of course, the interactions are weak. No, okay. This is being used numerically in traditional numerical methods. And how does one solve those kinetic models? We go back to particles and say, oh, so you say, that's weird. We started from particles, let n go to infinity, get an equation, and then we discretize it and we have particles, except that are not the same particles. The particles don't have equal weights. The weight is related to the size of the solution, and so on. So that's what I call macro particles. Could there be an idea like that with neurons? Okay. This is far, or macro nodes. Okay, but in order to go in that direction, we first need to understand what is the first side of the picture before we go to a discrete level. It turns out, I don't have time to go too much in the details, is that you can see neural nets as the number of nodes go to infinity, seen as a dynamical system, either discrete or continuous, on the space of priority measures. Unfortunately, thanks to Wasserstein, beginning of my lecture, and what we did in on Minfield games, we know how to do the analysis. What is the connection? So the connection is that when you have endpoints with symmetry, or endpoints with symmetry plus randomness, you can represent those endpoints by an empirical measure, which is always, independently of the number of particles, a probability measures. And it turns out the analysis on probability measures can be really, you can mimic the analysis that is bound in Rn. I've built this in many of my courses at Collège de France. In particular, the optimization, the control of this dynamical system, and this was, in fact, the reason we went into that was because of the large deviation for random matrices, and that's a subject I talk about in my last visit here. Of course, no one remembers, don't worry. Huh? I barely remember it. So, but I want to say that the loss function, which is now represented by a cost function on P, means that in theory, we have the mathematical apparatus to optimize the equation at the level on priority measure, and then we need to go back to neural nets. But there is one difficulty there, that if you take all flows on the space of priority measures, it is much too big. So you need to understand some of the operations which are being done to one layer to layer. What does that mean in terms of measures? In order to restrict a little bit the class of flows you have to write. So we have begun this tedious exercise, which is like building some dictionary to translate. And this is not entirely obvious. For instance, multiplying an n vector by a constant means a dilation of the measure. That's the simplest one. And so a positively homogeneous of degree 1 operation, which happens quite a lot, because there are linear combinations, there are max operations, and so on, means that you restrict yourself to transformations of measures that commute with dilations. Okay? What are those? well, mathematically that can be analyzed, but that's certainly not the right time to do that. It's, as I said, it's really ongoing. It's like a pet project that I have on the side, and from time to time I think about it. I have very little positive feedback about it, even among my collaborators, which are entirely convinced, once more, that I'm not totally healthy from a mental point of view. And I agree, it may be completely useless. Okay, this attempt may be useless. In fact, I love this. Well, anyway. But we have to do useless things in order to be sometimes lucky and maybe do something useful. That's not, of course, not me, but globally. So what I'm trying to say is that we need to understand better the global behavior. We understand a little piece, but the global pictures of neural nets. It's extremely important, and we can even stick to the simplest possible situation. Not necessarily generative AI and so on, which bring in a lot of stuff. It's as if when we were dealing with finite element computation, we would start immediately with a flow around the plane. Okay, no, we started with a linear equation in a square, in a ball, and so on. And we need to start from scratch here, because there is nothing in terms, in my knowledge, in my appreciation, there is nothing which goes into the direction of a much better understanding. And as I really emphasize this point, in that there is a lot of buzz about AI. It's not going to go away. It may not be the revolution that some people are saying. I don't know. We'll see. I'm always suspicious, because if we take the numerical world, no one has ever predicted what's going to take place in 5 or 6 years from now. Okay? So why should they know better now, this time? Okay? So we'll see. But it's being used, and there are dangers. So bottom line, we need to understand it. You cannot count on stupid politicians. When I say stupid, I could replace stupid by French politicians. That's both work. Sorry, I know you don't like that, but I cannot resist. I mean, we have a new prime minister every six days. I mean, it's how can you resist? It's quite exceptional. So anyway, of course, I have no idea what I was saying. So I guess what I want to say is that who will control those things? Cannot count on companies making tons of money out of it. Cannot count on politicians, which are at least complacent. So citizens, yeah, but it would be that would be really news if citizens were being listened to. But I think modestly, we're knowing that we have very little impact. Scientists have to play to get into that. That's my conviction. That's on social, on the social part, and on the math part. If you are a mathematician, there are thousands of fun questions, and I mentioned the Johnson-Lindau-Strauss lemma, because that's quite. It's funny when the first time you hear it. No, it's impossible. Epsilon to the exponential of epsilon square, but that's the correct answer. Which means that there, as a Nobel Prize in Economics said once, there are much less strategies than there are players. Huge numbers in the population, but in the end, most do always the same thing. So the dimension reduction is there. Okay, enough blah blah. I hope you survived. There was the only good news was that there was very little mass, and but the bad news is that we need much more mass. Thank you very much.
Thank you very much, Professor Liang, for sharing your insights about the interplay between AI and math. So let's open the floor for questions. Do we have any questions? I see many hands. Should I go to the students first or the...
Yes, the students first. Those guys are...
You choose. I will let you choose.
Thank you, Professor. I have one question. Do you have some advice for students or the young scientists who just started their career to use the AI tools? because as a postdoc, I always feel guilty when I use the AI tools to help my research, because it feels like a cheating in the test. Yes, thank you.
Okay. Many things. Okay, so, yeah, thank you. So, again, I love, thank you. I love historical perspectives or semi-historical perspectives. And in fact, I was mentioning finite element methods. What happened? What happened for structure, if we take the analogy with numerical computation, what happened with, let's say, structural mechanics? The physics of, let's say, linear type models were well understood, mechanics were well understood, the mathematics and the finite element method was completely under control. Software was produced by companies because in the end, to have a user-friendly, companies are much better than universities. Engineers start to learn to use the software in schools during their studies at master level. Then we go into companies, made computations. I remember seeing such computation about the vibration along the Ariane 5 launcher, a rocket. And from time to time, we would say, well, we have a problem. Maybe it's this screw, that tiny piece that makes a problem blocking the... and so I said, well, first of all, what model are you using? And the immediate reaction was writing down the discretize along a finite element method model. And so that's our model. They were thinking numerical models, which means that they had no idea that behind that, they had lost completely the idea that behind that are fundamental equations. And those equations were completely lost. I told them, but what about the equation? Oh yeah, we saw them in school, but they have forgotten everything about it. Which means that when facing a difficulty, they were lost. I think that this story might be valid, I don't know, but might be valid nowadays. You need to be to learn to use those new tools, like people needed to use the software or need to use the big statistical software if they're doing statistics. SAS, when we were young, was the premium. Now it's old, okay, that's my age. And so on. They need to learn it, right? But they need to learn something else, which doesn't come from AI. Now, it's true that AI can solve your exams pretty well, huh? But that's cheating. I'm sure that many students here have a friend who is slightly better in math and could do the job better than they do. But that's cheating. So yes, they should learn to use it. No, you cannot do everything. A friend of mine, in fact, it's the husband of a friend of mine, is a professor in computer science. And for the master, at the end of his course, master level, he gave the same exam to his class and to ChatGPT. And he was completely impressed when he realized that ChatGPT had produced one of the best copies in his class. Okay, so that's life. Because also passing an exam there is a lot of mimicry in an exam. It's not original creation. All this is that I understand very well both your scruples and the fact that people need to be able to use it and also to be able to criticize it. And so use AI if you want, but try to show me that it's a correct answer. Okay? There was another lady, a young one, not this old man. Oh, no, but we can always talk afterwards. So.
Thank you, Professor Liang. I was actually very excited when I saw a couple of mentioning of high dimension calculations in your slides about how potentially AI could be helpful in running computations as such. I asked Professor Haraj a question earlier this morning about superstring field theory, because it kind of feels like something that might have a potential in solving the questions, well, the mathematical questions in theory as such, either through experiments.
Okay, I'm a skeptic. I've not seen example of a real original creation using AI in math. Physics, I have no idea. Very original. Something slightly original, yes, there are examples. So then it's a matter of appreciation, evaluation, and Serge in a minute will ask me a question and will complement my answer because he knows about physics, I don't. So I doubt that. I think also it depends on which part of mathematics you're interested in. For instance, things which are related to formal computations, formal calculus, I have no doubt about that. Problems which are in geometry, in some part of geometry, not differential geometry, typically algebraic geometry, number theory, there is lots of analysis there, so it depends very much. In fact, some help could come from AI. I don't know how far this can go. Analysis will take much more time because it's not about identities, it's about inequalities. So dynamical system, differential geometry, and of course, the analysis we love, how we analyze. Of course, we believe that it's much more difficult and AI will never succeed. So there might be a cognitive bias there. But honestly, I think there is a matter of equality is something which is static, something with an inequality is there is infinity all over the place.
Sorry, I have a follow-up question. So are you saying that neural networks...
Be careful, because you understand that if each time someone asks me a question, you get a 10-minute answer. So we might be still there at 7, right?
Just one follow-up. So is it possible, well, is it not possible for the technology, even if in future state, to be able to propose new system or new theorems from a mathematical perspective? Because it's, I think of a mathematician, the Indian Ramanujan. Yes, because he barely had much of a formal education as he was growing up. And then, you know, he single-handedly then derived a lot of the theorems.
Remind me, in which year was that?
I'm sorry?
You remember in which year this was?
1940s, 50s, something
even
like that.
Before.
Yeah.
Huh?
1910.
And that's my answer, is that math has become, okay. Someone asked John von Neumann. John von Neumann is my hero. You've heard that story. Some of you have already heard that story. He was my ultimate hero. He was asked in the 20s, how much math do you know? And it was von Neumann, who had looked about thousands of questions and even more than most mathematicians know. And his immediate answer was 28%. Okay? So late 20s, von Neumann, 28. The mathematicians nowadays, any mathematicians, know much less than 1% of math. He may have some vague ideas about a bigger portion of math, but it's a vague idea. So, which means that the field has grown tremendously, and while you could have a genius like Ramanujan doing something more than a century ago, I doubt this would be possible nowadays. Of course, there are some Hollywood movies showing a janitor solving issues that he never learned, but that's a movie, that's a Hollywood movie. So I don't think it's possible, and I don't think it can serve as an example that computer systems can make. There are lots of examples of computer systems making quite complex proofs. the color theorem, but also some, I forgot the name in algebraic geometry, which are computer checked proof by a software which also has been computer checked by another software which has been proved to be correct. So we are very far from that in artificial intelligence. We cannot even reproduce twice a complex numerical operation. Okay, so doing rigorous math, complex math, which is not a formal rewriting of formulas and so on, I'm not very optimistic with generative AI, but one never know.
Thank you so much.
Thank you, Rachel. Professor Liang, thank you. Could we give a chance to the senior fellows, please?
Yeah, you may have a comments and questions.
Two weeks ago, I had a chance to discuss this with Jeff Hinton. I apologize, he got a Nobel Prize for that last year. And I was surprised because I don't know which point of view you can take, either much more optimistic or much more pessimistic than we are. He says that artificial intelligence can overcome human intelligence, that it will be creative, and I was really, I think if he's right, it's very bad. For example, he said that it's already discovered new deep theorems, and you just said that you don't think so. Okay, so it's consolation for me.
So, okay, maybe I also won't have exactly the same evaluation of what is a deep theorem.
No.
So it can do, it can do certainly, they can do complex statements and so on, but that's not what I call deep. Complexity and depth is not the same thing.
No, another question I have concerning the energy consumption. There is a huge difference between the energy consumption of this kind of machine and our brain. And so, but then I think a baby uses about a few watts to do what you need megawatts with a machine, but our brain is made of physical neurons. So what Hinton said is that the progress is so rapid that maybe one day the machine would be able to achieve the same kind of...
Okay, that's a very important comment. I didn't want to go into that, but thank you, Serge, because there are two ways to look at it. One way is to say, okay, so our neural nets are shitty compared to the ones that we have in brains. The other thing is that everything that happens in animal species results from evolution.
Yeah.
And typically, you were thinking about the human brain. It's absolutely amazing what a spider, which is both almost blind and has 6 eyes, can reconstruct, piece the information, piece all 6 information to get some perception of what's going on. Ants, I mean, there's probably 1 or 2 cells, brain cells, and they can do things without absolute effort, which would mean for us, walk on a straight line. Compare what they can do compared to what we can do would mean that we would be able to walk for 2,000 kilometers in a straight line in Sahara. We're completely unable to do that. So evolution did the job.
Yeah.
So did the job to provide, so the training was made in the evolution. Once training is made, neural nets are not consuming a lot of energy, except generative AI, which is crazy. But the use of neural nets doesn't consume so much energy. So maybe what we need is to think more to try to do as evolution did.
It's what.
So I don't know what is the correct
This
answer.
is what I tried to argue with him. I told him that the evolution, that silicon networks are less efficient than protein and DNA networks because they have this evolution built in. But he said, but this we can teach this machine to have this in there.
Yeah, that's true. In fact, this goes back to von Neumann. Von Neumann, at the end of his life, wanted to create evolutionary digital life. Okay,
Because I think one of his main points is that once the machine gets self-conscious, it will try to protect itself against, to survive. And in desperation, I told him, but you just have to unplug it. And he said, no, no, that doesn't work that way.
I love science fiction. I don't know. I really have no idea. But it's an interesting point of view, which means that some people indeed believe in the singularity time when machines overcome humans. I don't believe it, but who knows?
Thank you, Professor Haraj. Thank you, Professor Lians. That's very interesting debate.
This guy is going
Yeah,
to
here's
be
another.
tough with me.
I know, I'm not ending it. There's another question over here as well.
I'm going to be very grateful.
Thank you.
But it's going to be long.
Thank you. As a chemist doing protein crystallography, and for all protein crystallographers in the world, we have experienced a fantastic revolution coming from AI. This is, you have mentioned it, it is AlphaFold. It got the Nobel Prize. And I have two questions and one comment. The first question is, this revolution, it's a real revolution. To explicit it, today, I mean, until now, we needed huge synchrotron machines to get structures, three-dimensional structures of proteins. And now it takes 1 second to give the protein sequence and get the three-dimensional structure. So it can be a revolution in which we will close synchrotrons and use the computer to do the same thing.
Don't close them too quickly. You never know.
My question is, my question is this revolution used some special mathematics or not at all? And then I have a second thing.
Sorry.
The disappointing thing is that this revolution did not absolutely solve the understanding of how a protein sequence translates into a three-dimensional structure. So we have not learned anything in terms of the basic mechanism, so that actually a lot of people have challenged the Nobel Prize, saying that we did not understand anything about protein folding. It is just a tool and not some basic increased knowledge. So do you know any, and that's my second question, do you know any example in which, besides applications, tools, AI has really provided an increase in basic knowledge so far?
I'm not aware. Doesn't mean it doesn't exist. That's the first point. Second point is exactly what I was trying to mention, is how to create reduced models. So we did it on a very simple example. Okay, we saw the numerical results. We realized that most of the time the type of priority measures that were being used depended on 3 or 4 parameters, and so from infinite D we could go down to 3 dimensions. So this is not about understanding better, because I think we had some mathematical understanding of the equation, but saying what really counts, which is also part of the understanding. The word understanding is vague. Okay, so that was on a very simple example. I'm sure there must be other examples if you ask the questions. But most people that use AI don't even ask the questions. Say we can solve it, and so what? So I agree with you. That's why I defined myself early on as a skeptic. And I think also this exchange, I'm sorry that we are forcing everybody to listen to 3 old people discussing about physics, chemistry, and math. I hope this presents some interest. But for me, I think this is a very interesting source of discussions we can have at the IAS, and there are not so many places where we can have such discussion. And with that, thank you very much for your hospitality. I'm done.
I was going to open up one more question, but okay. Thank you, Professor Liang. Thank you very much. Thank you all. Thank you all, everyone, for coming to this lecture. We'll have more lectures this week. Thank you.